Hello, welcome to my channel. So this is my second video on electrostatics. So in my first video I uh, discussed about electrostatics in some basic manner, like what is an electrostatic field, what does it do, what does it deal with, why do we study electrostatics, what are its applications. So in my second video I'm gonna revisit those things, and then I'm gonna talk about flux, electric flux, and then talk about Gauss's law, then talk about voltage, uh, electric field, the field, electric field potential, and how its gradient is electric field intensity, and then talk about um, energy stored in an electrostatic field. So let me first discuss about what field even is. So in mathematics and physics term, a field is a region in which a particular physical function has value. We can measure it, we can measure its effects, its we can measure its presence. Okay, so field is obviously a physical thing, is a physical phenomenon, and it exists in 3D space in a region. So it is a particular physical function, obviously, which has value, measurable value, at each and every point in that region, that 3D space. So in modern physics, uh, we have force fields, meaning fields that has value, and that value is the value of the force, the magnitude of the force, the direction of the force, and many things. So force fields are very fundamental in physics and in the making of our universe. And as an engineer, electrical engineer, we deal with electromagnetic force fields. All the devices, electric machines like generators, motors, manipulate this force field generated by the force field, which is the electromagnetic field. So electromagnetic field is a fundamental fabric of reality. So force fields are physical entities that permeate in 3D space and mediate force between objects. So in a region where the force field exists, or the force field in a region is very significant, if an object is placed in that region, it will, given certain characteristics of that object, it will certainly feel force from that force field due to interaction. So all fundamental force in physics, for example EM field, gravity, strong and weak force, all the fundamental force, four types of forces, are described by their respective force fields, meaning besides electromagnetic force fields, the gravitational field, there's gravitational field, strong weak force, strong and weak force fields, which exist inside atoms, in nucleuses. So they are also fields. They can be described by fields. Gravitational waves and gravitational fields also exist. So in modern physics, field is more fundamental than particles, and each force field has corresponding field carriers, which are fundamental particles themselves. So excitation or perturbation, any disturbance in a force field, can be thought of as a particle, the intrinsic particle of that field. Like EM fields are vector fields obviously, and EM fields are mediated or carried by photons. Interestingly, EM field has field force carriers as photons, not electrons. So it's very interesting, but we detect the effect of electromagnetic fields via electrons, not photons. Electrons themselves exchange photons, and that is what we call electromagnetic field effect. So photons may be the force field carriers or intrinsic field excitators or mediators, the as particle, but the detection and manipulation of these fields is almost 90% done by electrons. So uh, when we say we are studying electromagnetic fields, we are basically studying the interaction of electrons, the manipulation of electrons, and and also fields also exist beyond particles, as modern physics proves it. Quantum dynamics proves that fields are more fundamental. They can exist even in vacuum, where where particles do not necessarily exist. So there's also gravitational field, which is considered a tensor field, and has a force field carrier graviton, which is theoretical thus far. It is not proven that graviton exists. And also strong and weak force fields are gauge fields. This is quantum mechanics thing. I don't know much about this myself, but these are gauge fields and has gluons as fundamental force carriers of strong and weak nuclear force fields. There are also bosons, and that's it. I don't know much about those. So basically these are fields and their particles. So my focus will be on the electromagnetic fields and its classical representation for most parts. So uh, I am I will be discussing about electromagnetic fields, and now I am focusing on the electrostatic field, which is a part of electromagnetic fields. So now what I'm gonna do is I'm gonna discuss about flux and how electric flux corresponds to electrostatic force fields. So now what I'm gonna talk about is the concept of flux. So force fields by themselves store energy and momentum in them, and the transfer of this energy and momentum can be visualized and even measured or calculated by what is called flux. So by definition, in terms of electromagnetic force fields, flux, phi d and phi b. Phi d is the electric flux and phi b is the magnetic flux. So phi d and phi b are by themselves scalar quantities. So they are just values, magnitudes. They don't have any direction or any complex matrix form like tensors. So phi d and phi b are scalar quantities in electromagnetic fields, uh, and flux, electric and magnetic fluxes are inherent properties of the fields. They are not inherent properties of particles like electrons and charges like ions and etc. So they're field properties. So uh, electric flux and magnetic fluxes are scalar quantities which indicate total field effect of a charge distribution whether stationary or dynamic, projected through a surface. So fluxes are always uh, measured by surface integrals and surfaces. Okay, in simple terms, surface of any type, surface of any type. So fluxes quantifies how much force transfer permeates through that surface, representing the field strength. So as I am focusing on electrostatics, thus I will be focusing on electric flux. And electric flux phi d measures electric flux strength. So electric flux phi d measures electric field strength. And we can also visualize it, or at least approximate the electric field and force transfer by the electric field and the electrostatic field in 3D space. Electric fields arise from free charges, like electrons, or charge q in general, positive or negative, and bound charges, like electrons that are not free, like free charges from conductors, etc., and bound charges from insulators, like dielectrics. Electric flux phi d per unit surface area in 3D space is flux density d. So flux density, uh, so electric flux can be expressed in terms of flux density, electric flux density. And if I wanna describe flux density in terms of electric field strength, electric field, it will be d equals to epsilon e. So this is flux, this is this is flux density, and this is electric field intensity or field strength, the actual field, the actual force field. And this is a quantity which describes the material or medium interaction with field. So fields are fundamental. I have told you beforehand. Fields exist even in vacuum, where there's no material or uh, no medium, so to say. A vacuum is mediumless. So electric field, when interacts with a medium or material, it is a force field, so it has flux. So its flux is affected by the material parameter, which is measured using this term epsilon, which is permittivity, electric permittivity. So electric permittivity is very important. Now we can express flux, electric flux, not only by its flux density, but by the electric field intensity, the electrostatic field itself. So electrostatic field is the flux, and And so this is the measurement of the electric flux. So flux is kind of a flow, so it can come in various types. So this kind of flux through a surface, say this is a surface, so this is surface. So this kind of flux is this is a cylindrical flux. This kind of flux has no sink or source, and if flux is seen emanating from a point, this kind of flux, and so from emanating and going through a surface, because surface flux is defined by a surface obviously. So this kind of flux is divergent flux, and if flux goes towards a point, so this kind of flux, this is surface, so this kind of flux, this is called convergent. So cylindric, this is divergence less, or you may say this cylindrical. This is cylindrical flux configuration. This is divergent flux configuration. This is convergent flux configuration. If flux is permeating and circulating a source or sink, this kind of flux configuration is curling. So this is curling flux or circulating flux, this kind of flux. And there's also another kind of flux. So this kind of flux is, this is uh, a combination of divergence or convergence. It can be convergent and curling. So this kind of flux is the combination of divergence or convergence and the circulation of flux. So flux can be these types: divergence or convergence less, or source or sink free. Source, emanating from source, divergent flux. Convergent flux, fluxes are gathering, or flux is kind of flow of something. So this is flowing into a sink of some sort, into a point of convergence. So this is convergent flux. um, the curling of flux and the combination of divergence and curling, or convergence or curling. So flux can be this 1 2 3 4 5 types. So now that I have talked about electric flux and uh, flux types in general, so what if I have to classify electrostatic field and its flux orientation, what kind of flux orientation does electrostatic field have? So electrostatic force fields have uh, flux orientation which is divergent or convergent. So charges can be two types: positive or negative. Positive charges are uh, said to have divergent force fields. So they have emanating fluxes. So you need charge to have a field. Okay, charge and spin in electromagnetic fields, I have forgot to tell you that we need charge and spin for electromagnetic field to be established and to interact with the electromagnetic fields. So charge and spin are very much fundamental to electromagnetic field interaction and establishment. So electrostatic fields, when positive charge is positive, the field electrostatic field is divergent, and it's divergent basically. It doesn't have any curl, and the positive charge acts as a source, and it has also a counter. Its opposite is negative charge, and as positive charge has divergence flux, negative charge has convergent flux. So convergent flux, so positive charges have divergent flux, hence uh, electric field is directs towards outwards. The force field directs toward outwards, and the positive charge acts as a source of electrostatic field, and negative charge has convergent. So the electric field, the force field the directs inwards to the charge, so the negative charge acts as a sink of the electrostatic field. So these are basic flux visualization. So these are flux lines, phi d, phi d, phi d. So now what I'm gonna discuss about is in my next video. So that's it for this video. So I have discussed about flux, force fields, flux, and flux density, and how flux looks like. So this is in 3D space. Okay, in 3D space, the flux obviously permeates through 3D space. So this may look like 2D, but it's I am describing the flux and field in 3D space, so don't forget that. Okay, so this is basically in 3D space. Flux is emanating or terminating in 3D space. Okay, like this, or in like this, from all from uh, all around from 3D space. So this is basically basics of electrostatics, electric flux, electric flux density. So flux per area or per surface is the flux density, and electric flux density is related to electric field, the force field itself, the electric field intensity, by epsilon. So epsilon is called the electric permittivity. Electric permittivity is very important. As my last topic in this video, I'm gonna talk about permittivity. Electric flux is related to the electric field by the material property, or property of the medium. So uh, which is quantified by the uh, term called permittivity. So or electric permittivity, this expressed as Greek letter epsilon. So permittivity is a fundamental property of material, so it is a material property. So from material to material, this um, property changes, hence not all material interact with electric field the same. uh, that's what this epsilon in this epsilon uh, tells us. So uh, the permittivity describes how much electric field uh, can build up in a material, or electric field is resisted in the material. So epsilon or permittivity quantifies how much charge can be polarized or rearranged in a medium or material. So it is a very important term, and epsilon is expressed as the permittivity is expressed as this. So the permittivity is the product of relative permittivity. This is called relative permittivity, and this is the permittivity of free space. Permittivity of free space is 8.854 into 10 to the power minus 12 force per meter. So permittivity is force per meter. So this is per, uh, the permittivity of the free space or vacuum. So permittivity is very important to understand.